To finish up this section, we'll look at 3 more identification numbers and coding schemes. First, let's take a look at bank identification numbers. The U.S. banking system uses a variation of the UPC coding scheme. A bank identification number is 9 digits long. The first 4 digits identify the bank's Federal Reserve District. The next 4 digits identify the specific bank, and the last digit is a check digit. So here we can label the 9 digits A1 through A9, and then our rule is going to be that the check digit A9 is the last digit of this weighted sum. So I've got 3 different weights in this sum because I'm multiplying my digits by either 7, 3, or 9, and then adding them up for A1 through A8. So let's take a look at an example of a bank routing number. The First Chicago Bank has the routing number 071000013 on the bottom of all of its checks. And we want to confirm that this is a valid bank identification number. So we're going to use this rule and make sure that the check digit A9 is correct. So first I'm going to fill in my chart with my digits A1 through A9. So my routing number is 071000013. So now I can put these digits into my rule. So I'm going to have 7 times 0 plus 3 times 7 plus 9 times 1 plus 7 times 0 plus 3 times 0 plus 9 times 0 plus 7 times 0 plus 3 times 1. So if I add that all up, that's going to give me a sum of 33. Then according to my rule, the check digit A9 should be the last digit of the sum, which is 3. So I should have A9 equal to 3, which it is, so this is a valid bank routing number. So how good is error detection with these bank routing numbers? Well, this coding scheme is going to detect all single-digit errors where just one digit of the number is wrong. More errors are going to be detected with this coding scheme than with the UPC coding scheme because we have 3 different weights, 7, 3, and 9, instead of just 2, where we had 3 and 1 for the UPC code. Again, there's a little bit of trouble with transposition errors. Most of them of this type, ABC to CBA, where I'm switching the first and third digit in a group of 3 digits, will be detected. But this error is not going to be caught if I'm switching a 0 and a 5 in this way. My next coding scheme is called the CODA-BAR scheme, and this is what's used by all major credit cards. A credit card number is 16 digits long, with the last digit being a check digit. Some other places also use this coding scheme, such as libraries, blood banks, and the South Dakota Driver's License Department. So let's look at the rule for the CODA-BAR. So we've got a 16-digit credit card number, so we're going to label the digits A1 through A16. Now we've got an intermediate step here. To look for errors, we first have to count the number of digits in the odd positions, which will be A1, A3, A5 up through A15. So I've got an odd index number here that are larger than 4, and then we're going to call that number T. Then once I know what T is, the rule for the CODA-BAR scheme is that the check digit A16 is chosen so that this sum, where I've got 2A1 plus A2 plus 2A3 all the way up to 2A15, and then I'm adding on T and my check digit A16, this whole sum should be evenly divisible by 10, which means that it should end with a 0. So this is a kind of complicated one. Let's take a look at an example of a credit card number. Suppose a company wants to issue a credit card with this number, 6432-8517-9490-517X, where X is the check digit. What should the check digit X be? So first I'm going to fill in my chart here with all my digits. So I'm going to have 6, 4, 3, 2, 8, 5, 1, 7, 9, 4, 9, 0, 5, 1, 7, and I don't know what my check digit is. I'm just calling that X for now. So we need to follow this rule, and the first thing we need to do is figure out what T is. So remember we said that is the number of digits that are larger than 4 in odd positions. So we're going to look at all the odd positions. A1 is 6, which is larger than 4, so that's going to count. A3 is 3, that does not count. A5 is 8, that's larger than 4, so that's going to count. A7 is 1, that's not going to count towards T. A9 is 9, that will count. A11 is also 9, so that will also count. A13 is 5, that's larger than 4, so I'm going to count that. And A15 is 7, which is larger than 4, so I'm going to count that. So if I count those all up, that gives me 6 digits in odd positions that are greater than 4. So I'm going to have T equal to 6. Alright, now I need to put all of these numbers into my sum, and this is what I'm going to get. So I'm alternating 2 times my digit plus 1 times the next digit all the way up to A15. Then I'm adding on T and A16, and this is the sum I get. So if I add up everything except for the X, I'm going to get a total of 125, so this is equal to 125 plus X. Now my rule is that this sum should be evenly divisible by 10. Well, the next number that's evenly divisible by 10 is 130, so I want to have 130 be equal to 125 plus X. Then I can subtract 125 from each side, so that's going to give me 5 is equal to X, so my check digit A16 should be 5 for this credit card to be a valid number. So how good is this credit card scheme at detecting errors? We hope that it's really good because we rely on this to protect us from credit card fraud. So the CODA-BAR scheme is going to detect all single-digit errors where just one digit is wrong. It's also going to detect 98% of all the other common errors. What it is going to miss is the transposition errors of this type that we saw before, where I'm switching the first and third digit in a group of 3 digits. And the algorithm used to compute the check digit is called the Luhn algorithm. So that's the name for the rule that we're using, and it's named after IBM scientist Hans Peter Luhn, who created it back in 1953. Finally, we're going to take a look at International Standard Book numbers. Most books published since 2007 have a 10-digit ISBN code and a 13-digit ISBN code. First, we'll take a look at the 10-digit ISBN. So the ISBN has some information about the book encoded in it. The first 1 or 2 digits are going to indicate the language of the book or the country where the book was published. The next few digits will identify the publisher, and the third group of digits will identify the specific book. And then finally we'll have a single digit at the end, which is a check digit. So these groupings of numbers that identify the publisher, the specific book, and the language or country will vary in length. But the check digit is always going to be just 1 digit. So let's take a look at the rule for ISBN numbers with 10 digits. So we're going to label the digits A1 through A10. And then for the rule, we're going to have this weighted sum where each digit gets a different weight, starting with 10 for A1 and then going down incrementally to 1 for A10. Then this whole sum should be evenly divisible by 11. So when I divide it by 11, I should get a whole number. So let's look at a short example of a 10-digit ISBN number. This is for the book Life of Pi. So here's the ISBN number 0. Then that's going to identify the country or language. 15 identifies the publisher. And then for the specific book, I've got 602732. And my check digit is 1. So let's check and make sure that that's the correct check digit for this ISBN number. So I'm just going to plug all of my digits into my rule with my weighted sum here. If I do that, they're going to add up to 143. 143 divided by 11 is equal to exactly 13, so it's evenly divisible by 11, and this is a valid ISBN number. So let's look at another example. Here we're going to come up with what a check digit should be for a book. So Springer Publishing Company wants to give the book The Science of Cooking the 10-digit ISBN number 354067466X, where X is going to be our check digit, and we want to figure out what that check digit should be. So here I've copied my rule down, and the first thing I'm going to do is fill in my chart with my 10 digits. So I've got 354067466, and then I don't yet know what my check digit A10 should be. So here I've just recopied that, and now I'm putting all of my digits into my rule. So this is the sum I'm going to get, and if I add up everything except for the X, that's going to give me 224. So this sum is going to be equal to 224 plus X. Alright, so now I need to find what digit I should have for X to make this evenly divisible by 11. So to do that, I'm going to fill in another chart here. So on the top, I've got my possible digits, 0 through 9. And on the bottom, I'm going to plug that in and find out what 224 plus X divided by 11 is. And I'm just going to round to one decimal place to fill in my chart here. So for 0, I'm going to get 20.4. 1 is going to be 20.5. 2 is also going to round to 20.5. 3 will give me 20.6. 4 will give me 20.7. 5 will give me 20.8. 6 will give me 20.9. For 7, I'm going to get exactly 21 with no decimal. For 8, I'm going to get 21.1. And for 9, I'll get 21.2. So here, 7 is the digit that will make this evenly divisible by 11. So my check digit A10 should be equal to 7. So what if none of the digits 0 through 9 had worked as a check digit? And this does happen occasionally. And in that case, you must have had to add a 10 to make the sum evenly divisible by 11. But 10 is not a single digit, so in that case, publishers actually use an X to stand in for 10 in that case. Just to go over the 13-digit ISBN very quickly, this is the same as the 10-digit ISBN with either 978 or 979 added to the beginning and a different check digit. And the 13-digit ISBN uses the same check system that we saw earlier with the 13-digit EAN number. So how good is this at error detection? Well, again, we're going to detect 100% of single-digit errors, and also 100% of transposition errors where we're just switching two digits. There are a few errors that are going to be missed, but nothing is completely foolproof, and this does catch the most common types of errors. That finishes up section 16.1. The things you should know: you should be able to use the rule for a scheme to tell if an identification number is valid. Also, given the rest of the digits of an identification number, you should be able to find the check number that will make it valid.